In Star Wars Episode 6 Return of the Jedi, we watched the Battle of Endor, where Rebel forces incapacitate the Empire's second Death Star over the moon of Endor. After the battle, Rebels are seen partying with the native Ewoks and celebrating their victory. But would they really feel so happy about the DS2's destruction? Would they even be around to feel anything? Would the Ewoks survive the destruction of the second Death Star over Endor? Through the fun of physics, we can find out. The first step to finding out is to state all our given information. By looking at this one shot from a scene earlier in the movie, we can compare the relative sizes of the DS2 and Endor. We know from Wikipedia that the radius of Endor is about 2,450 kilometers. By extrapolating from the shot, we can say that the radius of the Death Star is around 171.5 kilometers. We can also say that the orbital semi-major axis, or the distance between the centers of mass of Endor and the DS2, is 2,910 kilometers. We can figure out that the Death Star is 460 kilometers from the surface of Endor too. We'll also assume that Endor has a gravitational field strength of 9.8 meters per second, the same as Earth's, because people on Endor walk and behave the same as they would on Earth. Finally, we can assume that the density of the Death Star is 770 kilograms per cubic meter, the assumed density of an aircraft carrier. Now we have to find the mass of Endor. We can do this by comparing Endor's properties with Earth's using this nifty equation. The mass of object 1 divided by mass of object 2 is equal to radius of object 1 squared times gravitational field strength of object 1 divided by radius of object 2 squared times gravitational field strength of object 2. We can plug in all known values, including Earth mass and radius, and we find that the mass of Endor is about 8.8125 times 10 to the 23rd kilograms. For reference, Mars is about 6.39 times 10 to the 23rd kilograms, so Endor is actually more massive than Mars. It is also about 15% as massive as Earth. Next, we want to figure out if the Death Star is using technology like repulsor lifts to stay in orbit, or if it is in unaided synchronous orbit. According to Kepler's third law for a satellite in unaided orbit, the orbital period equals 2 pi times the square root of the orbital radius, or semi-major axis in this case, cubed over the gravitational constant times the larger object's mass. Using this equation, we find the orbital period of the DS2 would have to be 1.13 hours if it used no repulsor lifts. This would also have to be Endor's rotational period, as the same part of Endor is always facing the Death Star, and no spherical satellite can stably rotate that fast. Therefore, the Death Star must be using repulsor lifts. We'll assume that orbital period is 1 Earth day, 24 hours, because Endor seems to have a 24-hour day. Okay, so now we want to know if the Death Star can maintain its orbit without the aid of repulsor lifts. The Death Star is currently traveling at a tangential speed of 212 meters per second. By plugging known variables into an equation to find the needed orbital velocity, we can find that the DS2 needs a velocity of 4,494 meters per second to maintain orbit. With such a low velocity, the destroyed Death Star 2's orbit will decay rapidly, so its fragments will effectively plummet straight into Endor. It's important to note that when we time the explosion, it takes about 39.71 seconds for the Death Star 2 to explode after its reactor has been hit, much more time than the first Death Star took. We can therefore assume that the explosion is more gentle and very little of the metal is actually vaporized. We'll assume the fragments have the same total mass as the intact Death Star 2, the main difference being that there are no functional repulsor lifts anymore. Now let's find the Death Star's mass. We know the density and radius, so we can use the density equation to find mass. The Death Star's mass ends up being about 1.63 times 10 to the 19th kilograms. This is where the fun begins. Here we can find the mechanical energy stored in the Death Star using its gravitational potential energy before it falls. We find that its mechanical energy is equal to about 7.35 times 10 to the 25th joules of energy that it will transfer into Endor during the collision. For reference, we can find the mechanical energy of the Chicxulub asteroid, which caused the Cretaceous extinction, and that of the dinosaurs, by calculating its kinetic energy from known measurements. Its energy is about 2 times 10 to the 23rd joules that was transferred into the Earth. The Death Star 2 transfers about 400 times as much energy as the asteroid that killed the dinosaurs. Some simulations have shown that the crater that would be caused by the mass of the second Death Star falling on Endor would create a crater 700 kilometers in diameter, over 4 times bigger than the Chicxulub crater in the Yucatan. This incredible impact, combined with the fact that Endor is much smaller than Earth, only 15% as massive, likely means this collision would render extinct any and all life forms on Endor, including the Ewoks. But don't worry, if the colossal impact of the space station into the moon doesn't kill everyone, the radiation from the explosion of the Death Star 2's hypermatter reactor surely will. So for a quick and very oversimplified tutorial, radiation is basically just energy emitted from something like a nuclear bomb. If it is ionizing radiation, it is dangerous. A measurement of 4 to 5 sieverts is considered a lethal dose of radiation for a human. Also, because radiation is often electromagnetic, it follows the inverse square law. This means increasing the distance from the source reduces intensity by the distance increase squared. So doubling the distance reduces intensity by a factor of 4. According to this graph I found in the NASA archives from 1959, in space you could receive 100 Rankins or 11,402.5 sieverts worth of radiation from the detonation of a 20 kiloton bomb 45 kilometers away. That means it has 20,000 times as much explosive power as a ton of TNT. If we figure out the factor to which we're expanding that distance, 460 kilometers over 45 kilometers, we can use the inverse square law to see how much radiation intensity decreases by the time it reaches Endor's surface 460 kilometers away from the Death Star. It's about 110 sieverts. Earth's atmosphere renders 90% to 99% of all radiation harmless, so if you assume Endor's does the same, we find that someone on Endor's surface would receive about 1.1 to 11 sieverts from a 20 kiloton bomb 460 kilometers away. Remember, 4 to 5 sieverts is lethal. So the biggest bomb in history was the Tsar Bomba with a yield of 50,000 kilotons, 2,500 times as many as the last bomb we looked at. This means if the Tsar Bomba were to detonate where the Death Star was, the Ewoks would experience 2,750 to 27,500 sieverts of radiation. For reference, 4 to 5 is lethal. Keep in mind that the Death Star 2 would likely release way more radiation than Tsar Bomba. The DS-2 uses a hypermatter reactor. There is no easy-to-find canonical comparison between nuclear reactions and hypermatter reactions, but we can assume hypermatter releases much more energy since it fuels the Death Star's superlaser and all the hyperdrives in Star Wars. There's nothing like it that we know of in our universe. Side effects of this amount of radiation may include bone marrow destruction, leading to anemia and compromised immune systems, extensive damage to the gastrointestinal pathway, causing nausea, vomiting, diarrhea, dehydration, malnutrition, and electrolyte imbalances, extensive damage to the nervous system, causing confusion, disorientation, seizures, loss of consciousness, severe burns and skin damage, destruction of reproductive organs, leading to sterility, circulatory collapse, cardiovascular failure, acute radiation syndrome, mass suppression of the immune system, total organ failure, complete and irreparable destruction of every single DNA strand in your body, and a whole bunch of little tiny dead Ewoks. So yeah, they're dead. Sources include Dave Mitten's paper. He was the one who figured out like all the collision stuff. Wikipedia, ChatGPT, NASA archives, and Google. Thanks, everybody.